object-based methods for feature extraction. In the previous sessions, you have been exposed to pixel-based classification methods or methods based on the pixel-based methods for extraction of features of interest. Today we will talk about some algorithms which are object-based, unlike the pixel-based ones. So we will start with image segmentation. This is the process of dividing an image into regions of related content. So any related pixels will be grouped together with the help of a logic or algorithm. We can also say that this is a process of partitioning the image into some non-overlapping but meaningful regions, and these regions should also be homogeneous, that is corresponding to one type of pixels or one class of objects or features. Then in other words, we can also say the operation or the act of partitioning the image into a collection of connected set of pixels. So this could be into regions which usually cover the entire image. It could be other structures like linear structures, for example line segments or curved elements. Some shapes like closed entities like circles, ellipses, or long closed regions like ribbons, etc., and other symmetric regions. Now the requirement for these the implementation of these segmentation algorithms for clustering or dividing the image into different regions is that one needs high resolution satellite image, and these higher spatial resolution images have richer spatial content but less spectral content. The higher spectral content will be in the hyperspectral images. So segmentation algorithms are usually based on one of the basic properties of intensity values. This could be either discontinuity or similarity. Now if we focus on discontinuity, then we will be focusing on finding an abrupt change in the intensity, which will mean that we are looking for edges. So these are called edge-based methods. Alternatively, when we focus on similarity as the criteria or the basic property, then the partitioning of the image into similar regions will be based on a predefined criteria which will calculate the similarity of one pixel with the adjoining pixels. Now the first category of algorithms partition the image based on abrupt changes in intensity, as we have said. This gives us the edges in the image. So possible methods could be high pass filters like the Laplace filter or the Sobel filter, the Roberts filter, watershed based segmentation, or the Kirsch filter, any kind of high pass filter which provides discontinuities or abrupt changes in the intensity and thereby giving us the edges in the image. Then the second category, which is based on similarity assessment, are usually based on partitioning or categorizing or grouping similar regions together based on regions that are similar according to a predefined criteria. So the user chooses a criteria which could be any criteria, and the histogram thresholding approach also falls under this criteria. So possible methods could be defining a threshold by region growing, splitting, using split and merge, or a clustering method, or we could do a multi-resolution segmentation. Now in the next part of the discussion, we will be focusing on these algorithms, both discontinuity based or edge based and similarity based. So the main methods of this segmentation based on region segmentation are thresholding, region growing, clustering, and split and merge. So we are aware of the histograms. That is, histograms are constructed by splitting the range of the data into equal sized bins, which we also call classes. And then for each of these bins, the number of points from the data set that falls into each bin is calculated or counted. In the histogram here, the example that is given here, you can see that the vertical axis corresponds to frequency, that is the count for each bin, and the horizontal axis is the variable. So in image histograms, the pixels form the horizontal axis. So when we are adopting the thresholding technique, we determine the histogram first. The user chooses an appropriate threshold, and then labeling or classification based on this threshold is attempted. Once this is done, then the extraction of possible blobs by connecting similar components is done. So the histogram based threshold method will, the possible logic would be that one computes gray level histograms of the image. Then you focus on finding two clusters or two groups of pixels. We could begin with, say, for example, black and white. Then the error needs to be minimized so that corresponding clusters are related to similar pixels only. So one selects the initial estimate, and segmentation starts by using the initial estimate. The average gray level of each segment is computed, and then a new threshold value is then computed based on this. Then this continues until there is convergence, or the entire region has been identified into or grouped into similar based on the threshold. Now, for thresholding, we suppose that the gray level histogram corresponds to the image and is composed of dark objects in a light background, in such a way that objects and background pixels have gray levels grouped into two dominant modes. Now, one very obvious way to go about extracting the objects from the background would be to select a threshold T, as we have seen in the previous stepwise discussion. This threshold will separate these two modes. Then any point xy for it which fxy is greater than t is called an object point. Otherwise, the point is called a background point. So this is how the algorithm works. And see here, for example, we have a bimodal histogram. This is the example. We have a bimodal histogram. So if two dominant modes characterize the image histogram, it is called a bimodal histogram. If there is only one, so only one threshold is enough for partitioning the image. So here, as you see, they are partitioned into black and white, that is the background and the foreground, or the background and the object of interest. Now, if there is a multimodal histogram, that is, the image is composed of two or more objects. The objects are lighter than the background, and the background is dark. Two or three or more dominant modes will characterize the image histogram. So in such a case, if this happens, if we have more number of objects and the histogram is multimodal, then the histogram will have to be partitioned by establishing multiple thresholds. So multi-level thresholding classifies a point, suppose the point is xy, as belonging to any one of the object class. So then we will take more thresholds, right, and into the object class and then into the background class. Similarly, the grayscale image, when it has, you see the example here, this has a multimodal histogram because there are multiple shades of gray corresponding to this entire image. So, and then we have to establish a background. So after image segmentation, the output of the segmentation shows outlines of different objects or entities which make up the entire image. For example, the face, the hat, and shadows, etc. So it has also brought out if there are different shades of gray in, suppose, one object like the face, those have also been, because of lighting effect, etc., those have also been distinguished. Now the limitations or the problems with this approach are that there is noise. It could result in holes and discontinuities in the segmentation, and as we have just seen, due to illumination differences, so this is the face which should have come out as one segment. Because of illumination differences, there are multiple segments in which it has, or clusters into which it has been grouped. So this is one of changes in the illumination will also affect these, and we are not making use of the spatial information. Only the spectral characteristics are being used, and we are crudely classifying or clustering or segmenting the image based on these thresholds. Now, for the clustering methods, we take up K clusters, so they could range from C1 to Cn with corresponding mean values. Then the least square error will be defined by this equation, and out of all the possible partitions into K clusters, one has to choose the one which diminishes the least square error, or D value. Now the question arises, why don't we just do this? And if we could, then would we get meaningful objects? So if we are able to implement this, will we be able to get any meaningful objects by doing this clustering method? So some of the clustering methods are the K-means clustering and the isodata clustering. The isodata clustering focuses on selecting several cluster means and forms clusters. It splits any cluster whose variance is too large into separate clusters or groups. Then it groups together clusters that are too small and then recomputes the mean. This is repeated till the actions in points 2 and 3, that is splitting of two large clusters and grouping of very small clusters, cannot be applied any further. So to apply isodata clustering, the algorithm normally requires the analyst to specify the following parameters. That is the maximum number of clusters to be identified, the maximum percentage of pixels whose class values are allowed to be unchanged between iterations, also the maximum number of times that the isodata is to classify pixels and recalculate cluster mean vectors, minimum members in a cluster, maximum standard deviation for a cluster, and the split separation values. Then the minimum distance between the cluster means. These are the parameters which the algorithm requires, and these need to be fed into the algorithm. So in phase 1, the isodata cluster, the building uses many passes through the data set. So as you can see in the plots here, that the initial distribution of say 5 hypothetical mean vectors using a standard deviation in both bands is as the beginning and end point is used to start the initial distribution. Then in the first iteration, each candidate pixel is compared to each cluster mean and assigned to the cluster whose mean value is closest in the Euclidean distance. Once this is done, the second iteration with a new mean is calculated for each cluster based on the actual spectral locations of the pixel assigned to these clusters instead of the initial arbitrary calculation with which we started. Now, this involves analysis of several parameters to merge or split clusters. This decision has to be made. After the new cluster mean vectors are selected, every pixel in the scene is assigned to one of the new clusters. Now, this split merge assign process continues until there is very, very little change in the class assignment between the iterations. That is, the T threshold that has been used is reached, or the maximum number of iterations has been reached. If you remember, we had selected all these parameters initially. So here you see, this is the result. So distribution of 20 isodata mean vectors after one iteration, and the 20 isodata mean vectors after 20 iterations. So the feature space has been partitioned into 20 iterations. Then the second method is the k-means clustering method. So this is done by approximation to a hard combinational optimization problem, and it is an unsupervised method. So K stands for the number of clusters, and this is a user input into the algorithm. So from a set 0 data to or observations, k-means classifies them into k clusters. This is also an iterative algorithm. It is iterative in nature. So the k-means converges but finds the local minima of the cost function, and this works only for numerical observations. So fine tuning is required when working on image segmentation, when we use k-means for image segmentation, because there is no spatial coherency imposed in the algorithm. So it works as a starting point for more complicated or more advanced or sophisticated image segmentation algorithms. When we can use this as a basis for the image segmentation, which involves more advanced segmentation logic. So for an example, the k-means, if one applies the k-means segmentation or partitioning clustering method to this image, then we see that it has divided it into the trees, the sky, the grass here, and the building. But the buildings and the grass have been classified into or clustered as one cluster. And here also, if we see, the fountain, etc., has been segmented. Now, the next method is based on region growing. Now, region growing techniques start with one pixel of a potential region, and the algorithm tries to grow it by adding adjacent pixels. This is done till the pixels being compared are too dissimilar, then the growing stops. So the first pixel selected can be just the first unlabeled pixel in the image, or a set of seed pixels can be chosen from the image. So basically, to grow the pixels, the initial seed pixel has to be chosen. So it can be done either by choosing seed pixels from the image itself, or it can be unlabeled pixels in the image. So usually a statistical test is done to decide which pixels can be added to the region. So the homogeneity test that is applied is basically based on the pixel value plus minus the threshold, and pixel value variations from mean should be within a threshold. So this is how the homogeneity test is applied. So it starts from a homogeneous seed region, as you can see here. So you can take some sample initial seeds from either unlabeled pixels or the pixels in the image itself. So the region extraction is done by appending or grouping adjacent pixels which satisfy a similarity criteria. So basically you determine the seeds, grow regions, and then those regions are merged. So here this is the first growth step, and they keep on growing till the final segmentation is achieved. So homogeneity test is done, that is to test if the pixel intensity is close to the region mean value, and the thresholds vary depending on the region and the intensity of the pixel, right? So one has to choose an appropriate threshold. This is very, very crucial to the implementation of the region growing segmentation algorithms. Then the splitting algorithms, these start with the assumption that the entire image is homogeneous. The variance here is more than a certain threshold. If not, then the image is split into 4 sub-images. Now this splitting method is usually resultant in a blocky appearance. The split and merge method is actually the opposite approach to region growing, region shrinking or splitting method. So this is actually a top-down approach, and it starts with the assumption that the entire image is homogeneous. Now if we assume this to be not true, then the image is split into 4 sub-images, and the splitting procedure is repeated until the image is split into homogeneous regions. So the regions are examined to see if a valid region is achievable according to a similarity measure. If the region is consistent, it is accepted, else it is split into halves or quarters, and each new region is then examined. Then the splitting continues till all regions are consistent, and adjacent regions are examined and consistent regions are combined. So if you see here, the original image is taken as a square n by n having dimensions that are powers of 2. All regions produced, the splitting algorithms are squares which will have dimensions m by m again. Okay. And this process is recursive procedure. So after the first split, it is divided into 4 quadrants, right? Now this we can also describe by a tree or a quad tree method. So the first split, we have 4 resultant areas. The next split could give us, finds these as homogeneous regions, and the other 2 are split further into 4 regions. Then in the final merging step, similar regions are merged together, and the final segmented output is obtained. So this could be represented by the quad tree data structure also for region extraction. So it gives the breakup as a graphical image recursively from the root node. So if you see here, if we take up the same example, so this is the whole image, which is the root node with which we start. This gives us 4 quadrants, 1, 2, 3, 4. And then the second one, as we see here, has again been split into 4. Right. Now this root node represents the whole image, and this is recursively broken down into the leaf node, each of which represents a coherent region, as you can see here. So this is a coherent region, this, and then, so we had, after the first split, we had 4 quadrants. Then to complete the segmentation process, this must be followed by a merging phase. So as you see here, then these are further split. So this second node was split, and in the second step, this third node is split here. So this is the resultant quad tree, and the decompositions and the merging steps have been illustrated. So characteristic of the split and merge method is that is based on the algorithm given by Horwitz and Plavidis. This algorithm starts with the cut set of nodes, and these consist of 5 arrays which store the node properties. Now merging is done by comparing adjacent groups of 4 nodes with a common parent. Now if they obey the criteria, or if they fulfill the criteria, they are replaced by their parent node. Now similarly, splitting is done by breaking non-uniform nodes into the 4 child nodes at the lower level. When all the split and merge is complete, the final set must be grouped into regions. And as we have seen, the quad tree segmentation algorithms can be, a basic quad tree algorithm can be constructed by building a quad tree upwards from the image pixel and storing only the mean value of the subtree pixel in each of the nodes. To minimize the computation, the mean is computed as the tree is built. So you construct a quad tree storing at each node the mean for the child components, 4 child nodes. Search from the root of the tree to find the node which is highest in the tree and whose mean is in the required range. Then utilize neighbor finding techniques to merge adjacent node whose mean is again within the desired range. So with this, one has to do a uniformity linkage. So the image can be properly segmented by searching for the highest node within the required mean and variance range. One can save time by making a record of the highest uniform node in the each subtree as we go on along building the tree. The uniformity is recorded by adding one further pointer to each node in the tree, and this is called the U-link or the uniformity linkage. Now this uniformity is computed as per the steps that I will explain now. Now if a node is out of range, that is in variance, and all nodes in its subtree are also out of range, so one sets the uniformity linkage to null. Now if the node is in range but its U-link points to itself, so one sets the U-link to point to itself. So the node is in range, the U-link is pointed to, the uniformity linkage is pointed to the node itself. If a node is out of range but some nodes in the subtree are in the range, then the U-link points to the highest node in its subtree which is within the range. So these are the logic that is used to compute the uniformity linkage. So you can see diagrammatically U-link pointers that join nodes to the largest uniform node in the subtree, right? And therefore the quad tree is formed and segmentation is achieved. Now results here, you can see there are 2 examples given with the region grow, the region split method. So you see we had this some blocky appearances coming here, and this is the split and merge method. Now in the region growing method, you can also see that the illumination is affecting the output quite a lot. So you see here, all these are coming out as different segments. Similarly here in this example also, any difference due to illumination differences, that is coming out as, and this one is giving you very blocky appearance, the region split method. Now similarly, one can also segment lines and arcs or curves. So in some images, lines, curves and circular features are more useful than regions. So lines and arcs are often used in object recognition or for stereo matching purposes. So boundary based segmentation methods, which are based on edge detection, that is high pass filters like Sobel, Roberts, Laplace, and watershed segmentation. So watershed segmentation is a method which is based on the premise that we focus on a watershed or a watershed line. So the term watershed refers to a ridge that divides areas drained by different river systems in the natural system. So the catchment system is the geographical area draining into a river or a reservoir. Now when we interpret image data, it is analogy is taken for the image to be a topographic surface where gray levels represent the altitudes. So region edges will correspond to high watershed and low gradient will correspond to the catchment. So if we see here, these will be the catchment basins and these will be the watershed line. Now it produces more stable segmentation and continuous segmentation boundaries, and also provides a simple framework for incorporating knowledge-based constraints also. So the method is based on finding a downstream path from pixel of the image to local minima. Then the catchment basin is then defined as a set of pixels for which respective downstream paths end up in the same altitude minimum. Pixels are then stored in increasing order of gray values, and the catchment basin is filled from bottom, starting with the minimum altitude and successfully flooding the image. So if you see here, we had started by comparing the image to a natural watershed. So we have to establish, and the gray level values will represent the altitudes, with which we will define the catchment lines and the watershed lines. So basically we need to do a topographical interpretation. For this, the image is visualized in 3D and two spatial coordinates and gray levels are taken into consideration. The gray image is a topological image. Now for topographical interpretation, the points belonging to the region minimum is taken. Then catchment basins and watershed lines are watersheds are defined, and then dividing into lines or watershed lines, as you can see here. Now the main objective is to find out the watershed lines so that we can attempt the segmentation. Now the regional minimum and then to flood the entire topography at uniform rate from below. So if we go back here, once the catchment basins are identified and the watershed lines are also identified, then we can produce continuous segmentation boundaries. So this is one example. So this is the initial image, and the gradient lines or the catchment basin is defined, because as we are saying, with the set of pixels where the respective downstream path will end at the minimum altitude. So those lines, topographic surface has been defined based on the pixel values. And pixels are stored in increasing order of gray values. Now the second part of the discussion focuses on how to do segmentation with object-oriented image analysis. Now the difference between object-oriented image analysis based segmentation or classification methods is that, as in the previous case, we had seen that we focused on single pixels as units for classification. Now here the basic processing units are not single pixels but image objects or segments. Now this method uses soft classifiers, for example fuzzy logic, and not on hard classifiers like the ones we have seen previously. Now object-oriented segmentation makes an attempt to describe relationships in terms of spectral and spatial information, which considers not only the spectral characteristics of a single pixel but also the characteristics of its surrounding pixels. That is why it is an object. So it is not based on single pixels as your supervised and unsupervised classification algorithms were based, but based on a group of pixels which are called image objects or segments. So the basic processing units, as we say here, become image objects. That is why it is called object-oriented image analysis or object-based segmentation. Now object features, or simply said, they will be groups of pixels with similar characteristics or properties such as color, shape, area and scale. So these objects or groups of pixels will have similar properties based on any of these characteristics. Now multi-resolution segmentation is one of the very commonly used and popularly used methods. The multi-resolution segmentation is a bottom-up region merging technique, starting with one pixel objects. So the premise is that we start with a one pixel object, and in numerous multiple subsequent steps smaller image objects are merged into bigger ones. So they keep forming larger objects. The merging decision is based on a local homogeneity or similarity criteria, and this describes the similarity or homogeneity between adjacent image objects. Now if the smallest growth or increment exceeds the threshold defined by the scale parameter, then this process stops or the iterations stop. That is, the merging of the objects is then no longer done. Now throughout the segmentation procedure, the entire image is segmented and image objects are generated based on several criteria which you get of homogeneity in color or shape, and these criteria can be adjusted based on the thresholds that you apply. Now homogeneity criteria can be based on either it could be a spectral or color based homogeneity. So spectral or color based homogeneity of the object, the image object, is computed as the sum of the standard deviation of spectral values for each layer. Each layer meaning each band, and multiplied by the weights for each layer. This is the equation. So the color criteria is computed as the weighted mean of all changes in the standard deviation for each of the bands of the M bands of the image data set. So for each band from the M number of bands, this color criteria will be computed. Then the standard deviation are weighted by the object size, that is the number of pixels. So the homogeneity for color will be calculated, and as we see here, it is computed as the weighted mean of all the changes in the standard deviation. So mg here means merge, so that merging will take place. Then similarly, the heterogeneity criteria for shape heterogeneity or dissimilarity, this was for color heterogeneity, and the second one is for shape heterogeneity. So based on shape, how can we describe or define heterogeneity? This is done based on two parameters, that is compactness and smoothness. The equations for which are given: L upon square root of n, this is compactness, and smoothness is L upon B. Now L is the border length, n is the number of pixels forming the length, and B is the shortest possible length of a box bounding the object. So with these parameters we can define the shape heterogeneity. So heterogeneity criteria we have seen for two characteristics: spectral or color heterogeneity, which as we have seen it is computed as the weighted mean for all the changes in the standard deviation for that band of the all the number of bands in the image data. And we can also calculate a shape heterogeneity based on compactness or smoothness. Now the multi-resolution hierarchical segmentation, this is the example taken from the one logic or algorithm that is implemented in the e-cognition software. The hierarchical segmentation using fractal net evaluation approach. Now if you see here, this represents the idea of hierarchy as fractal nets because of their self-similarity notion of the fractals. So as we know, fractals are entities which are self-similar. So each coarser level gets the input from the finer level. Now if an object is identified at coarse level, then it repeats its representation at the finer level. Now as you have seen, we are saying that they are self-similar because this logic is based on fractal evaluation. So each coarser level gets the input from the finer level, and therefore if the object is identified at the coarser level, then it will repeat the same representation at the finer level also. Now the process starts with each pixel as object and then merges based on the criteria in which the merged regions should not exceed a defined heterogeneity threshold. So the heterogeneity threshold is defined and it merges based on this criteria and goes on merging till that is not exceeded. It is within the threshold. Now this multi-resolution hierarchical segmentation based on the fractal evaluation approach has the capability to incorporate spectral, textural, spatial, shape, size and a priori knowledge along with contextual properties of the image. Now we can vary, the user can vary the heterogeneity criteria, test them and then arrive at a logical input for the heterogeneity criteria and the scale parameter, etc. So here as you see, these segments have been created. So at scale 35 you can see the size of the segments and segmentation after scale 15. So from this large image, this small segment has been taken and this is the example. So here we see this segment has been broken into several smaller segment because the scale factor has been reduced. Now according to the requirement, we will keep adjusting the thresholds and the heterogeneity parameters. Now there are several object oriented image analysis software available. Example of one we've already discussed. This is the eCognition software. We have the feature analyst software available in NV. IIRS Imagine has the Imagine Objective toolbox. Then there are several freeware. Two examples are given here, and one can also use open source software. The OTB is an open source project for remote sensing which can be integrated in QGIS, and the segmentation algorithms in the toolbox include watershed, k-means, etc. ILVIS is also a free open source software available with raster and vector processing capabilities. Then there are several other user-friendly tools for interactive workflow. Parbat is used for segmentation. Then there are Python libraries and several. There is one provided by GSFC NASA. Here this is the link. You can go and look at this. It gives you recursive hierarchical segmentation approach. So you can look up this link to see and test the open source tools available. Now with this I will just show you a few case examples. So here object-based image analysis was done to extract urban roads automatically by combining airborne laser altimetric data and high resolution satellite images. So laser data was filtered and classified. So you can see here that the data was classified from very high buildings, medium buildings, height-wise, flyovers and low buildings. Now you can see here that the flyovers and some roads and some buildings correspond to the same height values. Then ground or near ground, water body, and then after classification the roads were extracted. Now the problem that came here was that now here you can see this is the representation of the point cloud. So buildings, very high buildings, more height, and these flyovers and these buildings. So these, because they had the same height, were likely to mix together. So for this the image was also used. Now after the application of the rule set and doing object-based image analysis with the help of the rule set, the roads and the elevated roads could be separated. Also the buildings with the same height as the flyovers or the elevated roads, one was able to filter them out. Then another example is from the high spatial resolution imagery was utilized for tree detection. So the examples that were taken were, this is the study area, and so three types of objects were extracted, that is isolated trees like these, slightly touching trees, a number of trees if they were close together like here. So you can see here, and a group of trees or a tree clump. So these were the three typical cases, and this is the segmentation for the individual trees, slightly touching ones, and the clump of trees, group of trees. Then accuracy assessment etc. was done by comparing it to visually interpreted data and automatically extracted data. Same kind of rule set was applied to extracting buildings automatically in planned and unplanned areas. So as expected, after the fuzzy rule based classification was done, the buildings in the planned area came out much better with more accuracy, and it was to check the accuracy, a reference, it was compared to a reference set of buildings. In the unplanned area, the inaccuracies were more, and it was felt that possibly more multi criteria could be applied to it, and the accuracy could then be improved. This is what the error analysis indicates. Then another example of performance analysis by feature identification. So the performance analysis of the segmentation was also attempted. Not just the performance analysis of the classification algorithms, but how well is the segmentation performing for the feature identification, because once the segmentation is done, we will classify. So the output that we get for segmentation also influences the accuracy of the classification. So these are done basically based on goodness measures, that is distance index measure, which is the closeness in the defined space to the ideal segmentation results in the context of a predefined training set. So for all of these, the examples that were taken were the for the building, for water body, trees, roads, vehicles and airplanes. These were the 4 or 5 objects that were taken. So buildings, water bodies, this is the water body, tree examples, roads, vehicles, these are slightly small objects, so can vehicles be segmented, and aircrafts. Then the first set gives you the actual FCC, and these are the outputs for the fuzzy segmentation. This is for the multi-resolution segmentation. Spectral difference based algorithms, the multi-threshold algorithm and contrast filter algorithm. These were the algorithms that were attempted, and some 5 or 6 object features were done. So segmentation for all of these different features with different algorithms was assessed based on the goodness measures that we have listed here. So distance index method, the area based methods, so the calculations were done based on these 4 criteria and calculated for all of these mentioned objects through the 6 algorithms. And the location based method, which is a Euclidean distance based method, and the Euclidean distance has been calculated between the centroid coordinates of the reference object and the centroid coordinates of the segmented analysis. So the conclusion was that the features with regular boundaries, that is man-made features, will give better results in the multi-resolution segmentation, and features with irregular boundaries are most likely to display better results with the fuzzy segmentation. So irregular boundaries will usually occur in natural objects like forest boundaries, or say soil boundaries, agriculture field boundaries, and field boundaries will be man-made. So agriculture field boundaries, roads, buildings, etc. Multi-resolution segmentation is most likely to give better results, whereas if we focus on natural entities or natural objects, then the fuzzy segmentation would be a better option to follow. With this we come to the end of the lecture. Thank you.